Assalamu alaikum and good evening everyone. Myself Moni and currently I am pursuing Masters of Science in Electrical and Electronic Engineering from American International University Bangladesh, which is in short AIUB. I am also working as a teaching assistant in the Faculty of Engineering at AIUB. Today my presentation topic is about graphene-based terahertz patch antenna for breast tumor detection. So in this slide I have the contents of my presentation, which are introduction, objective of the work, terahertz technology, 2D materials, literature review, methodology, result and discussion, conclusion, and at last the references are given. Introduction. So breast cancer is potentially life-threatening disease and it is one of the most common cancers, especially for women. For fast and effective treatment, early detection of the tumor is very important, but the frequent checkup is not possible for many people with the traditional ways such as ultrasound, X-ray, MRI because they are expensive and not always available for regular checkups. So this article proposes a cost-effective alternative using graphene-based terahertz patch antenna for early breast tumor detection. So the next slide is about the objective of the work. The primary objective is to design the lightweight antenna using novel material, and the secondary objective is to analyze the performance of the antenna in breast tumor detection. So the next slide is about the terahertz technology. Here in this slide in figure 1 we can see the picture of terahertz band, where the 10 to the power the terahertz band utilizes between 10 to the power 11 to 10 to the power 13. And why terahertz band is chosen? The terahertz electromagnetic waves operate in the frequency range of 0.1 to 10 terahertz, and these waves are valuable in biomedical application due to their low energy and minimal damage to tissues compared to X-rays. And terahertz waves are used in spectroscopy imaging and wireless communications. So in this slide is about graphene. Here in figure 2 we can see numerous number of materials are given as 2D material, but for this work the graphene is chosen. And why graphene is chosen? Graphene is a two-dimensional material with exceptional properties because it has high electron mobility. A higher electron mobility means that the material allows the electrons to move more freely, which is desirable in semiconductors for faster and more efficient electronic device. Here we can see that the electron mobility of graphene is greater than 2 lakhs square centimeter per volt second. And the ultra high current density, a current density of 1 into 10 to the power 9 ampere per centimeter square indicates the material can support very high levels of current over a small cross sectional area, which is crucial for high power and high performance applications. And high thermal conductivity, which is 5000 watt per meter Kelvin. A high thermal conductivity value such as 5000 watt per meter Kelvin means that the material is very efficient at transferring heat, which is important in application where heat dissipation is critical, such as in electronics and high power devices. So these properties make graphene an ideal material for the design of terahertz antennas. Let's move to the next slide. So this slide is about the literature review. Numerous articles were followed for this work and some of them are presented here. So here in article R. Hassan et al. We can see that they have designed an antenna which is the 80 by 80 millimeter square, and the task of that antenna was to go COVID-19 affected lung detection using the ultra wideband frequency. And R. Alloy et al. Also designed an antenna which is 15 into 21 micrometer square, and the task of that antenna was to breast tumor detection. And M. Shalini and M. G. Madhavan also designed an antenna which is 50 by 50 micrometer square, and the task of that antenna was to multiband operation. And MAS MD Azani and Z. Jainul Abidin also designed an antenna which is 200 by 200 micrometer square, and the task of that antenna is breast tumor detection. And M. Dashti and J. De Carey also designed an antenna which is 40 by 40 micrometer square, and the task of that antenna was utilized in terahertz communication. Let's move to the next Next slide. So in this slide, the flowchart of the work is given, where the work was started by collecting the graphene properties and the antenna was designed in CST by using graphene as patch material. After that, the terahertz bandwidth was and after simulating all the data were analyzed. When the desired result were got, then the phantom model was designed and the results were analyzed. From the analysis, detection of the tumor through the antenna was done. Let's move to the next slide. So the next slide is about the modeling of the antenna and breast phantom. Here in figure 4, we can see that the dimension of the antenna is given, and in figure 4b, the 3D view of the antenna is given, and in figure C, a portion of breast phantom is shown, and in figure D, port of the antenna is given. So here, while modeling the antenna and breast phantom, the proposed antenna was designed using CST Studio Suite, and the antenna size was kept 23 into 18 micrometer square, and the frequency range is kept 2 to 10 terahertz, and the material of the patch was chosen as graphene, and the breast phantom model was created to analyze the antenna's performance in detecting tumors of different sizes and positions. So this slide is about the result and discussion. Here we can see that in figure 5a, the reference impedance of the antenna is given. So the antenna is constructed with careful consideration to uphold a 50 ohm impedance match because it secures efficient power transfer between the transmitter and the antenna, minimizing power losses and optimizing signal transmission. For any operating antenna, the return loss value must be less than -10 dB. Here in figure 5b shows the return loss of the antenna in free space, indicating a minimum S11 value of -52.442 dB at 6.96 terahertz. Additionally, a voltage standing wave ratio value between 1 to 2 is considered acceptable. In figure 5c shows the VSWR value of the antenna in free space is 1.004785 terahertz at 6.96 terahertz, which is very close to the ideal value. Figure 5d shows the three-dimensional far-field pattern of the antenna in free space. The representation reveals that both radiation efficiency and total efficiencies are -21.35 dB and -21.36 dB, correspondingly, with a directivity of 5.294 dBi at 6.96 terahertz. Meanwhile, figure 5e shows the polar far-field pattern of the antenna in free space, depicting a primary lobe magnitude of 5.29 dBi. The angular span of the primary lobe is 98.1 degree, positioned at the main lobe direction of 19 degree. The numbers 5.29 dBi tell us how strong the signal is in the main direction, and the 98.18 degree angle shows how wide the area is that the signal covers. The main lobe direction at 19 degree indicates where the antenna focuses most of its signal. Let's move to the next slide. So next slide is about the antenna in normal breast. So here in figure 6a represents the return loss of the antenna when placed in normal breast environment, revealing a minimal S11 value of -51.187344 dB at 6.424 terahertz, which is less than -10 dB. So it can be stated that the antenna can operate in normal breast. Moreover, the VSWR value of the antenna in normal breast scenario is depicted in figure 6b, which is recorded at 1.0055317 terahertz at 6.424 terahertz, which is also near to the ideal value. Figure 6c showcases the three-dimensional far-field pattern of the antenna within normal breast environment. This visual representation includes that the radiation efficiency and total efficiencies are measured at -17.37 dB and -17.37 dB respectively, with a directivity of 6.424 dB at 6.424 terahertz. And in figure 6d displays the polar far-field pattern, highlighting a primary lobe magnitude of 6.32 dBi. The angular breadth of the primary lobe span 58.1 degree, positioned at inclination of 8 degree. Here in this slide, the results of the antenna for different sizes of the tumor is shown. Here in figure 7a, the phantom of breast with 2 mm tumor is shown, and in figure 7b, the phantom of breast with 3 mm tumor is shown, and in figure C, the phantom of breast with 4 mm tumor is shown, and figure 7d shows the return losses of the antenna for different size of the tumor. Here in figure 1 shows the performance of the antenna for different sizes of the tumor. The observation from the table reveals that when the tumor size is 2 mm, the resonant frequency remains constant, but the return loss shifts to minus 51.95 dB. Upon increasing the tumor size to 2 mm, both the resonant frequency and return loss changes, with the frequency shifting to 6.416 Terahertz and the return loss is minus 52.006 dB. Furthermore, with a tumor size of 3 mm, there is another shift in the resonant frequency, and the return loss is minus 50.9 dB. The directivity and VSWR of the antenna also changes for the different size of the tumor, which are shown in table 1. This indicates that as the tumor size increases, both the resonant frequency and return loss exhibits greater shift. As the antenna can operate effectively and provide distinct data corresponding to various sizes of the tumor, it has the capability to detect tumors of different sizes. So the next slide is about the different position of the tumor. Here in figure 8a, we can see that the tumor position is at center, and in 8b we can see that the tumor is in upper portion of the phantom, and in figure 8c we can see that the tumor is in the bottom portion of the phantom, and figure 8d shows the return loss of the antenna for different position of the tumors. Here in table 2, it shows the antenna performance for different position of the tumor, and the data indicates that when the tumor is located at position 1, the resonant frequency is 6.4 Terahertz and accompanied by a return loss of minus 50.9 dB. Shifting the tumor to position 2 results in the return loss of minus 50.6184 dB and at a resonant frequency of 6.416 Terahertz. Similarly, at position 3, the the antenna exhibits a return loss of minus 50.2729 dB with a resonant frequency of 6.408 Terahertz. VSWR and the directivity of the antenna also changes for different sizes of the tumor, which are shown in table 4 as table 2, as the antenna can operate effectively and provide distinct data corresponding to various sizes of tumor. It has the capability to detect tumor at different position. Now let's move to the next slide. Here in this slide, the comparison of the proposed work is done with some other published work, where it is visible that the proposed antenna is better in terms of size and return loss, and also in terms of patch material. Here is the conclusion. The proposed graphene-based terahertz patch antenna shows great potential for early breast tumor detection. It operates efficiently in both free space and breast tissue environment, and the antenna's lightweight design and low return loss make it a viable tool for early tumor detection. Further research and development could lead to widespread adoption in biomedical imaging. Here in this slide, the references are given for the proposed work. I appreciate your time and interest in my presentation. For any further question or inquiries, please feel free to reach out to me. And my contact mail is also given here. Thank you.